Good afternoon, everybody. We are going to be listening to another podcast on ionization energy, and you're going to see that it plays a part with the last one that you just listened to with atomic radii. With atomic radii, we talked a lot about that ZEF, that nuclear attractive force. And now with ionization energy, we need to overcome that. So ionization energy is the energy an electron must absorb to overcome its nuclear attraction and escape the atom, meaning how much energy does it take to remove an electron? So let's just write that here. How much energy So how much energy is needed to remove an electron? And that's what these next two equations are going to show you. So you can see that ionization energy to remove the first electron for lithium, I have lithium here, and I need 520 kilojoules of energy. And then you can see if that energy comes in, it's going to become a cation. Lithium, it'll lose that one electron. So what has happened here is I have my lithium going to Li plus 1. And if you look on your cation and anion sheet, you will see that that follows. You look up lithium and it will say plus 1. If you look at your periodic chart, it is in family 1, and that means it's going to lose that one electron to gain noble gas configuration. So I did say noble gas configuration. So second ionization energy is to remove a second electron. And look what happens here. For the same lithium, now that I have it it has a cation, it is going to take 7,297 kilojoules of energy. Now look at that difference. Wow, why? Well, this is because after lithium has lost one electron, it has now become a noble gas. Now, you don't need to flip over this in your notes, but I just want to grab a periodic chart here to show you. So if I take a look at this, you can see here's my lithium. If it loses one electron, it goes from 3 electrons down to 2, and now it's going to look like helium. And so it's not going to become helium, it's just going to have the characteristics of it and become very stable. We know that noble gases, excuse me, is what elements are trying to look like and mirror, and once that happens, they don't want to leave that state. And this is the situation here with the lithium. So if we go back to that slide, you guys can see that it easily loses this first electron, only needing 520 kilojoules of energy, which is 520 calories, which is not a whole lot. And then it's going to jump up to over 7,000. Now, why is this so high? Is because after losing Okay, so it's so high because after losing the first electron, lithium became stable. It became that noble gas configuration. It doesn't want to lose any more electrons. Okay, so ionization energies can be explained by electron configuration. If more stable configuration noble gas results, we have a very low ionization energy. So that happened with lithium plus 1. If they can get to this configuration easily, it doesn't require a lot of energy. If you are going to get a less stable configuration, then it's going to require high energy. So if we take a look at sodium and write down its electron configuration first, you would see that it's 1s2, 2s2, 2p6, 3s1. Remember, keep adding up all these superscripts. So I have 2 plus 2 is 4, plus 6 is 10, plus 1 is 11, and the atomic number for sodium is 11. If I draw its off-ball diagram, and this is increasing energy, I have 1s, 2s, 2p, and 3s. Then go ahead and put in all the electrons. 1s2, 1 spinning up, 1 spinning down, 2s2, 2p6, 1 in each orbital first, come back and fill, and 3s1. So we have that one lone electron sitting up there in that energy level. So in order to gain its stability, it can easily lose this first electron, easy to lose, and that's going to require low ionization energy because that's it's a metal. It wants to lose its electron. It wants to become a cation with a +1 charge. Now you can see that now it has become very stable. This is now noble gas configuration. It does not want to lose another electron, and it's going to be very difficult to remove that. So we have a general trend. If we look at our periodic trends, you guys can see that the first ionization energy generally increases from left to right. So that's what this is showing. From left to right, it generally increases. So that means that fluorine is going to be very, very hard to remove that electron. And remember that the nuclear charge increases, more protons, more pull. So as I go across, that fluorine, not only does it want to gain one electron to look like neon, it's not going to want to lose it, and it's a lot smaller. There's a lot more energy there. Metals, things to remember right here, metals have a small first ionization energy. So the elements on the left-hand side, they want to lose their electrons. Non-metals have a high. And that's what this is showing you. So the further you go to the right, the harder it is to remove your electrons. And those are general trends that we're going to continue to work on in class. Well, I hope you guys all are having a wonderful day and will continue to have one. And I guess I haven't said this on a podcast. Think like a proton, always positive. I'll see you in class. Take care.